Welcome, folks, to Triton programming tutorial. I've been thinking of making this series because uh, the resources on internet are not very clear. The documentation is there, but I thought I'll simplify it for the viewers. So basically, I want to make a series on Triton. This is the first video. We'll go in depth and cover a lot of Triton features. Okay, so let's get started. Basically, you can find Triton here, right? So you go to Triton programming language, and this is the documentation. All right, right. So this is where you can go and take a look at it. Yeah, so let's get started. Today, basically, Triton is used for programming your GPU kernels, right? So writing massive parallel programs, right? It's the interface is Python, but you have Triton is both like a language. Also, you can think of it like a compiler. So you basically you write Pythonic code, and the Triton compiler, which is a GIT based compiler, converts it into GPU optimized code, right? That's the high level thing, right? But yeah, it's a little different from CUDA in the sense that with CUDA you have to go very low level, like, but performance wise they are at par, and you get to write in Python. With CUDA it's more low level and you have more control. But yeah, um, that's the primary difference. But yeah, I mean the JIT compiler, Triton JIT compiler converts gives you highly optimized CUDA code, GPU code, which can and this works both with AMD based GPU and NVIDIA GPU, which is CUDA. Okay. All right. So, I mean, the first thing is you have to pip install Triton, which will. So I already ran it and it's already there. So I'm using Colab here, which is running on T4 GPU, right? So okay. Then you import Triton.language as TL. Import Triton, and then I'm importing PyTorch. Yeah, you have to install PyTorch also. So just do pip install torch, and that should install your PyTorch. All right. I'm here. I'm just checking if what sort of if GPU is available or not, right? So if basically I'm testing what the device is. I'll print it. Yeah, it says okay, I'm on CUDA. All right. Now the problem that we'll look at today is the most basic fundamental problem is let's start with the addition of two vectors. So let's say you have vector n and vector a and vector b. When you use Triton, it's going to parallelize the addition, right? And so here, so in Triton, everything that you do, you have to. So I mean, kernels are simply, you can call it functions, but yeah, in GPU parlance, you call it as kernels, which means is right. You write it's an optimized sort of function that is going to run on GPU. Here you decorate it with return.git and you write a. So the syntax is completely Pythonic. Now here it's taking two vectors, which are basically and with Triton you deal with pointers, similar to how you deal with NumPy, right? So it's very close to how you work with NumPy. Now it takes two input vectors here, x pointer and y pointer, and then I'm going to add both of them to pointer. And n elements is the size of each of these vectors. And in Triton, there's something called block size. So let me explain how this works so that you know understand. So let's say this is vector A. I'm assuming let's n is equal to this vector of size 20 elements, right? And this block size is you can define your own block size. So it's a constant that you define. Now what happens in Triton is it is basically going to and since it's a one-dimensional vector, 1D vector, it's going to, and it has n20. So now what it's going to do is it will do 20 by 3, right? Which is going to give you seven blocks. So basically, these seven will be run in parallel. So the first you take three elements because block size is three. It's going to take three elements from vector A and three elements from vector B. Add this, and then three elements in from the next three from vector A and next three from vector B, and going to add it. And all of these will be run in parallel. That's where the performance gain comes from, right? So you're not serially taking three elements from vector A and running and with vector. So what you're doing is because I've mentioned block size equal to 3 and n divided by 3 is like 6 point something. But yeah, to round it off, you'll need seven parallel program IDs. You call it program ID here, right? So first program ID is first three elements, and the next one is fourth, fifth, and sixth, right? So on. That's how it goes, and then all of these will be sent to CUDA in parallel, sent to GPU in parallel, right? And so block size is in n is equal to is equal to 20 is not in your control because it's the input vector A and B. But how you define this block size is up to you. So usually you take a large enough number, let's say 2 to the power of 10 or something, 1024 or whatever, right? And then you parallelize it, and it's all in one dimensional. Okay, so this is what is happening. It's now in this case, because n is 20 and block size is 3, we'll have 20 by 3, which is 6 point something, right? 6.66. But yeah, we would need 7 parallel chunks to be running, right? And that, so keep this in mind, and let's look at the code now. I think now it'll be clearer. Okay, so I'm taking this as my input x and y pointer, and since it's a one-dimensional vector, you do tl dot program id 0. If it was like two-dimensional, then you will have 0 1, right? Three-dimensional 0 1 2. But here is just one-dimensional. So and PID is basically on the x-axis how many of those parallel blocks you're running. In our case, we'll have 7 of those. So Triton will depending on what you define your block size and number of elements, PID will be dynamically generated when the program is running, right? So yeah, initially, so for the first block it'll be 0, for the next one it'll be 1, right? And that will become your offset when you are trying to calculate the pointers. Okay, cool. Now, right, for the first, as I said, where is your block starting from? In the first instance, because PID is, let's say, 0, so you'll have starting from 0 into block size is 0. So your block start is going to be from here. Then you calculate, okay, what is my next pointer? Your next pointer is going to be TL dot A range 0 to block size, right? Here in block size is 3, so it'll be 0, 1, and 2. So you're going to add block size, block start to this number, right? So that you get the all the three elements that you want, right? The pointer to those elements, and you call those offsets, right? Okay. Now that's it, right? Now also, why do you need mask? Mask is like just to make sure that your offsets don't go out of bound, because right, see, for the last block, the seventh block, you will have elements ranging from you will have n is equal to 20, but you can have offset 21 also, right? So when you do offset less than element, it's basically saying, okay, if I go out of bound, you stop the pointer there, right? So it's just to make sure that you don't go out of bound in that area. So here mask will be true or false depending on what your offset values are and what your elements are. So here our number of elements is 20. So the moment you get 21, it'll be false, right? So that's how it's to make sure that it doesn't go out of it, because pointers are crucial in Triton, right? Now, once you get the mask and once you get the offset, this is how you do TL dot load. Uh, Basically your, so the x pointer is basically your base pointer, and then you put offsets to it, right? So you do this offset that you calculated here, you put that offsets, and then mask is equal to mask. All right, so similarly you load you so now when you do load, this goes into GPU, right? Yeah, it is on GPU, but basically you're taking the first three elements of a pointer to the first three number in your vector, right? Then y is again you do the same thing, and then you add x and y, which basically is this, and then you write it back into the output pointer which I have here, right? So you do TL dot store output pointer, and then for writing it back again, you need offsets because you need exact pointers to where you're writing. So you do output pointer plus offsets, and then you put and also the where you are, so you basically are loading z into output pointer and then the mask. Okay, and then this whole function becomes your kernel, right? And you call it whatever I've called it at kernel, and you decorate it with return the git. And then block size here is again a constant expression size, which for example it's 3 in our case. Okay, now let me run this. So it just runs normally, it's just a function. Then to call this kernel, you need like a wrapper. So this is where I'm defining my inputs. So what I'm saying is, okay, basically X is my tensor, torch tensor, Y is also torch tensor, and output also going to be tensor, making sure that they are on CUDA. If they're not on CUDA, you put it on CUDA, right? And also making sure that the shape is, so this is just basic Python code or PyTorch code that you would write, right? So make sure that the shape is matching, otherwise you can't add. And then I'm generating an out which is dot empty, like because it has to be of the same dimension, and then finding out number of elements, which is out dot number of elements here. Once I have both of these, okay, so now to call this function, which is a kernel, Triton kernel, what you do is you define the grid first. So basically, grid is just a function, and then you say, okay, here what you're trying to tell is, okay, how many programs do you need, right? So in our case, we need 7, right? What I showed you here. because your vector is of size 20 and then you divide it by 3. This is what I'm doing there. So this is and it's called grid in Triton. Okay, so the grid is this how you define a grid. You define it like a lambda function, and then you are doing Triton dot division n elements. So let's say n is 20, and then there in our case block size. So this automatically when Triton launches it, it will fill the this meta is a dictionary and it'll get filled by block size. So you say, okay, this is my block size. So basically, when you call this, okay, so once you have this, this will be your number of grids that will run in parallel. And also because we're using, if it was a 2D grid, then you would pass one more element. We'll see that in the future. But right now, you pass. So this lambda returns a tuple, which is right now only one element here. But if depending on the dimensionality of the vector, you would fill in here. So it's basically I'm dividing n elements by the block size, and that will be 7 in this case. I mean, in 20 divided by 3, whatever. Okay. And how do you once you have grid, this is how you call the kernel. So you this is a syntax. You do add kernel and then you put the grid here, and then we are passing x, y out and elements and block size, right? So block size basically, as you see, all your keyword arguments will get passed in here, right? So because block size, I'm defining it like that, it'll automatically get in meta, and then that's how it'll run as a dictionary. You can call this is meta, you can call it anything, but yeah, this is how you call your kernel. Okay, and then finally, because I'm passing pointers here, this kernel doesn't return anything, but this pointer will automatically get updated here, right? So TL store will fill in my output pointer. All right, so now I run this. Okay, so now let's finally call all of this, right? So I've defined a main function and then setting manual seed. N is like one large number, and then I'm randomly initializing two random toy tensors x and y, right? With size 98432 of float 2032 types. So I have n, I have x and y, and then this is like I'm just testing. This is in PyTorch and this is in Triton. Okay, so in Triton vector, so I'm calling this function now, which I defined here. So it takes input x and y, and it should give me my output, right? So, uh, yeah, and then this is being returned. Yeah, so basically I call this vector out, and then I'm making sure that my this is in PyTorch, and this is, and so let me write it. Okay, this is using PyTorch. So this is vector addition using PyTorch. This is vector addition using Triton. Okay. Cool. So I get out and then I'm running. Let me run this. Yeah, so you see that both the output were exactly the same, right? And I can also print out. So if I do print out, you can also see. So you get some value, and this is on the file. All right, so yeah, this is how it works. The key takeaways is you define a program ID. So one along x-axis will be 0, and this will automatically Triton will fill PID, and you have parallel grids running, right? And each of these grids will execute in parallel, right? And then if the more dimensions you'll have to add PID along x, y, z, n number of let's say 3 dimensions. You'll have to add 3, and this is how you get pointers to it, you get offsets to it, and then you do the calculation. All right, I'll be this was the first video in the series. I'll go more in depth and try to cover practical algorithms like flash attention and things like that, more complicated stuff, so that you understand how Triton works. All right, thank you.